Welcome. Today we're going to be talking about kinematics, or the physics of moving things. So you can often find these problems in Physics 1 and just general physics. They're going to kind of give you the introduction to physics, and they're kind of what most people would think about when they think of physics. If somebody throws a ball, what happens to the ball? And so these formulas are going to help give us an idea of what actually will happen. So we have the final velocity is equal to the initial velocity plus acceleration multiplied by time. We have the final position is equal to initial position plus the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. We have the final velocity squared equals initial velocity squared plus 2 times the acceleration multiplied by the difference between the starting and the final position. And then last we have just kind of the average velocity is equal to the initial velocity plus the final velocity divided by 2. And so this is just, your basic definition of an average velocity. Now, by no means is this the full list, and is it everything that you're ever going to need to solve any kinematics problem, but it is a good starting spot. It will provide a good backbone to derive any other formulas that you need. You can mess with these a little bit just to make it fit with your problem, with the variables that you need to find, the ones you already know. So this is a good starting place. Now there are two things that we need to keep in mind when putting into use any of these formulas. First off, acceleration must be constant. Now we see here that acceleration is a linear variable that it just gets a little bit tricky if we try to put in a variable acceleration that's changing with time, because then we have a formula that's not based on one variable. We have a multivariable formula, and that's a little bit more tricky than we can put into use here. Second off, this is only for motion in one dimension. We can't mix and match our dimensions here. If you notice here, this has x for the position. This doesn't mean that you can only use this formula for things that are in the x coordinate plane. However, you do have to be very careful and consistent when using position. You can't say, well, the final x position is equal to the initial y position plus the rest of the formula. You do have to be careful and only use the same x or y or z or whatever your coordinates are. You have to use the same ones throughout. So let's go ahead and jump into our first problem. A car is initially traveling due north at 23 meters per second. A, find the velocity of the car after 4 seconds if its acceleration is 2 meters per second squared due north. And B, find the velocity of the car after 4 seconds if its acceleration is instead 2 meters per second squared due south. So, first off, let's check to make sure our prerequisites are met. It does look like the acceleration is constant because we do have a constant number here, and it doesn't look like it's changing direction, at least not within each individual question. So that prerequisite is met. Second, is it in one dimension? Well, I do see north here, north and south, so it is all in the same coordinate plane, and that meets our second prerequisite. So before we even get started, let's go ahead and make sure that we have our coordinate plane, we have our coordinate system all ready to go, so that we're not confused about any of the signs. So I'm going to go ahead and define positive to be up or north, and I'm going to define negative to be down or south. Now you can choose whatever coordinate system you like. It doesn't really matter, again, as long as you're consistent. It'll give you the correct answer either way. However, I find that sticking with the coordinate system that I remember easily to be more helpful, because I'm less likely to accidentally change afterwards. So north is defined as positive, south is negative. So let's go ahead and find which formula we can use. Well, here we have final velocity, which is what we're looking for, so that's good. We have the initial velocity, which we know, 23 meters per second. And we have the acceleration, 2 meters per second squared. And we do have time, 4 seconds. So this looks like it's already set up perfect for what we want to do. We're not even going to have to solve the formula for any of the variables. We just plug it in. So let's go ahead and get started with that. And we do know that the initial velocity is 23 meters per second north. And going back to our coordinate system, north is defined as positive, so that is going to be positive 23. And the acceleration in A is 2 meters per second squared due north. North is positive, so it's going to be positive 2 multiplied by time, which is 4 seconds. So let's just simplify this out, and we have 23 plus 8. And finally, we're going to come out to the final velocity is 31 meters per second. Now we go back before we finish and we wash our hands of it. We're going to go back and make sure that it does make sense. So we started off 23 meters per second going north, and if we accelerate north as well, after 4 seconds it should be some number larger than our initial velocity. It should grow, and that does make sense after a short amount of time that it would grow from 23 meters per second to 31 meters per second. So I would say that this looks correct. Next off, we have the same problem essentially, except in this case, the acceleration is the opposite direction. So if we look at our formulas again, we see that it does appear we can use the same formula, but we're just going to have to be very careful about signs. So let's go ahead and start that. Again, we're going to define positive as north, so our starting velocity is still 23. But this time, our acceleration is due south in the negative direction. So that 2 is actually going to be negative. Multiplied by the time, which is 4 still. And now it's just that same simplification. And this time it's going to be negative 8. So the final velocity for part B is instead this time going to come out to be 15 meters per second. Now again, let's go ahead and check to make sure it does make sense. We started at 23 meters per second north, and then we are decelerating. So we're accelerating southwards at the same rate of 2 meters per second squared for the same amount of time. So it does make sense that it would slow the car down, but not stop it and not change its direction, at least not yet. So I would say that this answer here, 15 meters per second, does make sense. So to go over, we've talked about kinematics, what they are, and the basic formulas that you can use to solve the problems, and just kind of the basic problem-solving technique that we can use. Now, there will be follow-up videos to this video with some more problems, solutions, and how to derive different formulas as well. So please like if this video was helpful, comment if you'd like to see me cover another topic, and subscribe if you'd like to see more physics help videos. Thank you. Have a great day.